Worked example 16, question 1a. An RL circuit with a resistance of 70 ohms and inductance of 0.2 henries is connected to a supply voltage of 100 volts, 50 Hz AC. Determine the phase shift of the circuit. So in order to determine the phase shift, we're going to have to work out our inductive reactance here, XL. We'll then have to work out our impedance, and then from there we can work out the phase angle, the phase shift between the voltage and current in the circuit. XL is equal to 2 pi FL, and 2 pi times frequency of 50 times an inductance of 0.2 gives us an inductive reactance of 62.83 ohms. Our impedance, Z, is equal to R squared plus X squared. And from previous examples, you'll remember that when we have only an inductor in the circuit and no capacitor, then X simply becomes XL because XC is 0. Z is equal to the square root of R, which is 70 squared, plus our reactance, plus our reactance, which we worked out to be 62.83 squared, and that gives us a total impedance of 94.06 ohms. To calculate our phase shift, theta is equal to inverse cos of the resistance over the impedance. So cos inverse of 70 over 94.06 gives us 41.91 degrees. Question 2. A RC circuit with a resistance of 2.2 kilo ohms and a capacitance of 1 microfarad is connected to a 200 volt 50 Hz AC supply. Determine the phase shift of the circuit. Capacitive reactance this time, which we can then use to work out our impedance, and with the impedance we can work out our phase shift. So our capacitive reactance is equal to 1 over 2 pi FC. So we can substitute our values in here of 2 pi times our frequency of 50 multiplied by our capacitance of 1 times 10 to the minus 6. And that gives us a capacitive reactance of 3,183 ohms, or 3.18 kilo ohms of capacitive reactance. Circuit impedance Z is equal to R squared plus X squared. X is equal to XL minus XC. Because there is no inductor within the circuit anywhere, then our XL simply becomes 0, leaving us with X being equal to XC. We ignore the minus for right now, that comes into play at a later date. So X becomes 3.18 kilo ohms, and therefore Z equals the square root of 2,200 squared plus our X of 3,183 squared, and our total impedance for the circuit is 3,869 ohms. Our phase shift is the inverse cos of the resistance divided by the impedance, so cos inverse of 2,200 divided by 3,869 gives us a phase shift of 55.4 ohms. Question 3. An RLC circuit is connected to a 400 volt AC 50 Hz supply. If the circuit resistance is 100 ohms with an inductive reactance of 150 ohms and capacitive reactance of 200 ohms, then determine each of the following. A. The phase shift between the voltage and current. B. The supply current. And C. The voltage drops over each component. Notice in this question that rather than being told the inductance in henries and the capacitance in farads, we're actually given XL and XC straight away. So we don't actually need to calculate these. This is something that can catch students out if they're just used to following the procedure of calculating XL. They'll just take whatever number they see here Students that have sort of learned how to answer the question by rote can get caught out by this sometimes. They'll take whatever information they're given here and insert it into the formula without thinking about it. Don't get caught out by that. If they're telling you the reactance and it's in ohms, then you don't need to work out XL and XC because you've already got it. To work out the phase shift, theta, we're going to need to work out our total impedance, Z. And with the total impedance, we can then work out our theta with cos inverse R over Z. So in this case, our overall reactance, X, will be XL minus XC. So in this case, it's going to be 150 minus 200, and that gives us minus 50 ohms of reactance. Now the negative here tells us that the capacitance, or the reactive capacitance, is greater than the inductive capacitance, and as a result this is going to be a leading circuit, and what we mean by that is it means that the current is going to be leading the voltage. Let's calculate our total impedance. Z is R squared plus X squared, root of all, and this becomes 100 squared plus our negative 50 squared. Now we put brackets around that, and the reason we can often ignore the negative is because when we square a number, if it's negative it becomes positive anyway, so it doesn't really matter. That negative only tells us, gives us a bit of information to tell us that the circuit is a leading current circuit. So our total impedance, we get 111.8 ohms. To calculate our phase shift now, we do cos inverse R over Z, so 100 over our 111.8, and that gives us a phase shift of 26.6 degrees. Because we know it is a capacitive circuit, this phase shift of 26.6 degrees we would then say is leading. Part B, we were being asked to work out the supply current IS. So IS is equal to the supply voltage divided by the total impedance of the circuit, and our supply voltage is 400 volts and our impedance is what we worked out earlier, 111.8, and that gives us a supply current of 3.58 amps. Part C, we're asked to determine the voltage drop over each component, and for that we've got three variants of Ohm's law. V equals I R, where we're going to be using the supply current and the circuit resistance. V equals I XL, where we'll be using the reactive inductance or inductive reactance, and VC, where we're going to be using IS times XC, the capacitive reactance. Voltage over the resistor equals our supply current of 3.58 multiplied by the resistance of 100, and that gives us a voltage drop over the resistor of 358 volts. Voltage over the inductor is again our 3.58, this time multiplied by XL. Remember, XL, we're told, is 150 from the question. And that gives us 537 volts. Finally, voltage over the capacitor is our 3.58 multiplied by our capacitive reactance, which was 200 from the question, which works out to be 716 volts. You will notice, or you may have noticed already, that the supply voltage is 400, and these three voltages clearly do not add up to 400, and in fact they are in some cases greater than 400 volts. That's okay, don't worry about that. We'll get into that in later examples. That's for something later down the line, but that is absolutely okay.